Fisher projections indicate stereochemistry. So these are a convenient way for us to sort of depict what could otherwise be very complex and difficult to interpret molecules. The rule for Fisher projection is that the horizontal bonds point out of the plane of the page. You can think like a bow tie sticking out from the surface. And the vertical bonds are pointing into the page. So it'll be drawn like this with just straight lines. But you should recognize that there's a specific orientation that suggests. So when I have the molecule drawn like this, I can in fact line them up. I can do my assign and align, and I can actually figure out an absolute configuration. When you're building these Fisher projections, you have to be really careful about your choices of direction. So you can't just arbitrarily put them whatever position you want, because the Fisher projection indicates stereochemistry. For example, these two Fisher projections are equivalent, but these two are not for the same molecule. One is R, one is S. So if you, for whatever reason, do have to rewrite or change the Fisher projection, it is really important that you keep everything consistent. If for some reason anything has to change, make sure that whatever you've drawn as your final result is actually the correct configuration. So just check its absolute configuration. Okay. Fisher projection is not particularly useful. Not that it's not useful, but it's not particularly intended for simple molecules like this, because they're relatively easy to draw. Fisher projections become really useful when we have much more complex molecules like these amino acids, or with these carbohydrates. Few people have sufficient artistic skill and or time to draw something like this. Okay? This took a long time to put together on the computer, and nobody wants to do that. This, super easy. Okay? So the exercise that I'd like you to do is to consider what is the absolute configuration, given the rules, of this carbon atom here. Note the one that I've highlighted in yellow. Note that this red bond is the same as this red bond. I just have it there for a frame of reference. So when I'm asking about this carbon atom, I'm also asking about this carbon atom. What is its absolute configuration? Is it R or is it S? Think about that for a moment. Okay, so this group, let's actually make some choices here. This OH is going to be 1, and this H is going to be 4. Again, H is always the lowest priority group. I have some tough choices to make around which one is 2 and which one is 3. So I have this carbon atom competing against this carbon atom. Who's going to win? Well, the top carbon atom, let me actually make them different colors so you can track them. The red carbon atom is attached to an OH, it's attached to an H, and it's attached to a carbon. The blue carbon atom is attached to an OH, an H, and a carbon. So they're equivalent. I'm going to have to move down the line to make a distinction. So next, I have this carbon atom that I'm going to compare against this carbon atom. Again, I'll keep the colors consistent. So the red carbon atom is attached to an oxygen. It's attached to another oxygen. These double bonds count as 2 bonds to an oxygen. And it's attached to a hydrogen atom. It's not drawn, but it's there. The blue one is attached to a hydrogen, attached to an oxygen, and attached to a carbon. Okay? The red one wins because it's attached to 2 oxygen atoms. Oxygen takes priority. The blue one is only attached to 1 oxygen atom. So the red one wins. And that means the red one is going to be 3. And the blue one, this bottom one, is going to be, oh, no, it means it's going to be 2. That's the next priority. And this one down here is going to be 3. So I've now assigned the priorities. I need to align them. I'm going to ignore number 4. And notice that they're all basically pointing at me. So I don't have to reorient how I'm thinking about them. I can just look at them. You can see that they are going counterclockwise. So this is S. So this carbon atom right here is S. Now, after we've done all that work, I'll tell you a little trick. For carbohydrates that are drawn in their proper Fisher projection, that is, the carbonyl is furthest towards the top, and normally carbohydrates should be drawn like this. When carbohydrates are drawn properly, the OH on the right means it's R. OH on the left means it's S. So this is R, S, R, R. Always. No matter what position it's in. Again, this is only true for carbohydrates drawn properly. So I don't have to think separately about this one being like, well, it's kind of further away, so does that change things? It doesn't actually change things. If it's on the right, it's R. If it's on the left, it's S. So that's a really quick and dirty trick for these. Okay. Newman projections also technically indicate stereochemistry, but that's not really their purpose. Their purpose is to indicate what we call conformation. That's orientation or shape in three-dimensional space. So, for example, if I'm looking at ethane would have these 2 methyl groups attached like this. Different conformers of ethane would have different twists around these bonds. It's still ethane. Conformers are the exact same molecule. They're just different angles of different shapes, contortions, or what we call conformations of molecules. So looking at this sawhorse projection, you can see I have the methyl group in the back, and the CCl, the COH, and the CH over in the front, the same molecule we've been looking at a couple times already. If I look down the angle or down the axis of this bond, right here, if I orient it so that it's pointing directly at me, it'll kind of look like this. So what we're describing here, what we're showing is a carbon atom right here in the middle, and a carbon atom on the outside. The other carbon atom is behind it with this ring. Okay, the vertex that you see right here in the middle is the carbon atom closest to you, is this one. And the ring, this carbon atom back here, is this carbon atom in the back. So I know from this Newman projection that I have a CH3 in the back because I have these H's attached to the carbon atom in the back, and that it is in fact this exact same structure. So different conformations of this structure, again, would have different angles around that bond. You can see that these conformations are not the same. The molecule is the same, but the angles around those bonds or around that bond are not the same. And in fact, there's a different favorability, energy favorability of certain conformations over others. So some conformations are more favorable than others. And we'll talk more about that when we get to steric-kindreds. Okay? You can see how Newman projections get really unwieldy really fast. And they're not really that helpful when the molecule gets incredibly complex. So we'll generally see these for smaller molecules when we just want to understand a particular bond at a time. I've got this little activity here for you. And I want to note that this is an activity that you would not reproduce on the MCAT. But this is still fun, and is valuable for us so that we're clear about a lot of these projections and structures that we've seen. What I'd like you to do is to match only those compounds that are identical. For example, if you think these B and F are identical, you match them. But to be clear, I only want you to match them if they are unambiguously identical. If they are definitely the exact same molecule, you match them. If there's any ambiguity, if they may or may not be the exact same molecule, don't match them. So go ahead and try this out, and when you're ready, we'll discuss. Okay, so let's look at the first one. CH3CH2OH. You should recognize that as ethanol. That's an alcohol, and it's 2 carbon atoms. It is ethanol. So there's our ethanol. And in fact, A is the same as K as well. I know it's the same as K, even though the Fisher projection is drawn differently, because it's not a chiral molecule. So the fact that I've reoriented it around the Fisher projection structure does not matter. It's not chiral, so they are the same molecule. B and F are not the same. B and F, it turns out, are actually enantiomers. They are mirror images of one another. C and I are the same. Again, this molecule is not chiral. It's achiral, so it doesn't matter that I've reoriented the Fisher projection. D and G are the same. They're different conformations, but different conformers are the same molecule. They're not different molecules. Different angle around the bond, but it's still the same molecule. And E and H, these are not necessarily the same. They might be, but this projection that I have doesn't actually indicate stereochemistry, so I can't determine whether or not they're the same. They might be, but they might not be. And so those are the only matches. Okay? Interpreting these structures and being able to generate these structures is important. Now, going deeper into stereoisomers, we've talked about one type, which is the enantiomer, right? The mirror image. So for example, we saw this long chain hydrocarbon before. It has these 10 carbon atoms down the chain. And we remember it had a methyl group, an ethyl group, and a propyl group on it. I know this is not a typical projection that does indicate stereochemistry, but I just want you to sort of bear with me, and let's pretend that it does. So let's pretend that this tells me it's R, this tells me it's R, this tells me it's S, just for the sake of argument. So if I make that assumption, R, R, S, the enantiomer, the mirror image, is going to invert all of the stereocenters, each of these chiral carbons, the stereocenter. So it'll be S, S, R. That's the mirror image. That's what it would look like in the mirror. But because I have 3 stereocenters, what if I only changed 1? What if I only changed 2, not all 3? Well, then I'd call them diastereomers. So a diastereomer is a stereoisomer where you've changed 1, but not all. So at least 1, but not all of the stereocenters. If there's only 1 stereocenter, then you've changed all of them, right? So it's just the enantiomer. But if it has more than 1 stereocenter, and I only change 1 but not all of them, then it's a diastereomer. So in this case, the diastereomer is SRS. Again, you can see it's not the mirror image, but it's also not the same as the molecule itself. So any chiral molecule can have only 1 enantiomer, only 1 mirror image, but they can, in theory, have many diastereomers, and carbohydrates are a great example. D-glucose has an enantiomer L-glucose, but they have many diastereomers, D-mannose, D-galactose, D-allose, and the L-isomers of those. Those are all diastereomers of glucose. So we've talked about stereoisomers. Structural isomers are molecules that have the same molecular formula, but they have different connectivity of the atoms. So these two molecules that I have here are structural isomers. They have the exact same molecular formula, but you can see that they're pretty different molecules. And conformational isomers we've seen, or conformers. These are the exact same molecule, just differing angles around the bond. I have this here just for reference, so you can sort of wrap your mind around the connections between some of these types. You don't need to memorize this or reproduce this, and in fact, it's arguably not very helpful. For example, why are diastereomers below enantiomers? Doesn't mean they're less similar, arguably not, right? Some of this is a little bit subjective, but we can see the different types of isomers that we've talked about.
For most students, and maybe you too, the CARS is the hardest section on the MCAT. It may feel like it's one of the few remaining obstacles between you and the medical school of your dreams. But as you try to prepare for the CARS, you find there is a never-ending stream of conflicting tips, strategies, and plans, none of which seem to actually help or show any results. If you feel frustrated, overwhelmed, or lost when it comes to the CARS, if you're looking for a CARS expert who has helped thousands of students achieve their MCAT CARS goals, then you found your solution. Testing Solutions MCAT CARS Bootcamp. Founded by Nick Zahner, a current medical student at Stanford with a master's degree in philosophy of religion from Harvard, Testing Solutions' approach to the CARS is revolutionary. Testing Solutions CARS Bootcamp provides day-by-day, step-by-step instruction that teaches you the techniques that produce ultra-high MCAT CARS scores. Instead of wasting your time with the needlessly complex filler that other companies try to sell you, Testing Solutions' approach to the CARS is based on the principle of minimum effective dosage. There's no wasted time, just the minimum amount of effort that is required to get you the results you want. With over 500 4.5-star reviews on Amazon, Testing Solutions CARS Bootcamp is the most trusted, proven, and effective CARS course available on the market today. You will have access to Testing Solutions' 180 meticulously designed CARS passages, the largest CARS practice library offered by any MCAT prep company in the country. Our passages are regularly rated by users on Amazon, Reddit, and SDN as the most accurate non-AAMC CARS practice passages available, consistently rated higher than Exam Crackers, the Princeton Review, Kaplan, and Next Step. Unlike some companies who prey on pre-medical student fears by charging outrageous amounts of money for their mediocre at best practice materials and courses, Testing Solutions will always charge a fair price for an amazing product. Because after all, we're not like the other test prep companies. We're aspiring doctors just like you, only a little further down the path. Let us help you do what we've already done. If you're not happy with your CARS Bootcamp for any reason, we offer a 100% money-back guarantee, no questions asked. You've got nothing to lose and the CARS score of your dreams to gain. Don't be one of the people who write us each week saying they wish they had found our MCAT CARS Bootcamp sooner. You don't have to struggle with the CARS any longer. Sign up and get started today.